spend too long because I know that many of you have seen this before, but maybe I'll show you a couple of new aspects of it. Seadragon is a multi-resolution system for interacting with visual information. This is a client and server technology, and what that means is that it's a system with two ends. One end is on the server, and that actually is trivial. And the more interesting part of it is client software that allows access to this visual information. And when I talk about visual information, I'm talking both about ordinary digital images, for example, like this one. This is a 6 or 8 megapixel image of one of the of a temple in Cambodia, I believe, and also more complicated kinds of objects. So somewhere around here, there's a very high resolution image, and this is by now a very old collection. So this is an image of about 300 megapixels from the United States Library of Congress. And as you can see, the interesting thing. Please don't applaud. Ask questions, but don't clap. The interesting thing. So the thing to notice, of course, is that the responsiveness of the software is the same, whether we're looking at an ordinary digital camera image or at a very large image like this. And the reason for that is very simple. It's not because of anything magic that the software is doing, but rather because of a real mistake that I think is being made in the way images are normally dealt with on the computer. Normally, I guess the way images were dealt with in the very beginning was a kind of raster-based system in which you store all of the pixels in the image, starting at the top left and kind of going in reading order until you get to the bottom right. And that's a ridiculous way of storing an image, because it means that you don't know what the bottom right of the picture looks like until almost the end of the entire image stream. And if the image is very large, then that could be a very long image stream. And you might have to wait for a very long time, especially if the source of that imagery is over a narrow bandwidth connection. Now, if you're actually interacting with an image on the screen of a PC, you don't need all of that information. You can either see an entire image at low resolution all at once, or you can zoom in and you can see only a small part of it at high resolution. You can't see the whole thing at high resolution at once. So the trick is very simple. It's just a matter of decomposing the image into what's called a multi-resolution pyramid, and this is a very old idea, which means that you have tiles of information about the image at low resolution, and then you break it up spatially into smaller tiles at higher resolution. In fact, let me show you what these tiles look like. I've just turned on a switch that as it brings tiles in from the server will actually color these tiles with random colors. And you can see that as those tiles come in, only the tiles are coming in that we actually need as we zoom in on different parts of this little world. So it's simply a dialogue. Instead of loading an entire image at once when we need it, we're only loading the parts of it that we need as we navigate. There's a continual dialogue happening between the client and the server. If you think about this kind of approach to applications in general, I think it's a very powerful approach, because it means that you're no longer limited in terms of how much detail you can access. It's absolutely unlimited. The total amount of bandwidth, the total amount of memory, and the total amount of processing power that you need is constrained by the number of pixels on the display, and that's it. And this is also a very powerful idea if you think about mismatches between the size of the imagery and the size of the display that you're working with. On the web, of course, we tend to only see images that are about 400 pixels across at most, because that's about how big things need to be in order to fit on the screen. But if you're browsing using, say, an iPhone or a small device like this, then the screen is no longer the right size to deal with those images, and so you start to have to do zoom. And Apple implemented zoom in a very beautiful way with the iPhone. But of course, they haven't changed by doing that. They haven't changed anything basic about the way the images are actually represented out there in the cloud. And if you instead do a more systemic change in terms of how those images are represented, then suddenly you're in a world where you can access the same kinds of images, the same kinds of visual information on very small screens or on enormous screens the size of a wall, on low bandwidth connections, on high bandwidth connections, it doesn't matter. You've broken all of those dependencies between memory, bandwidth, and so on. Okay, let's see. Now I had better turn off my special mode. This is so I have a couple of other kinds of content in this little collection which I can show you. One of them is content which is not in fact based on data but based on calculation. Many of you will recognize this object. It's a Mandelbrot set. It's a mathematical object. So this is an example of something that's being computed rather than accessed over the internet. And so this is just a little game or a toy, but it's designed to show you how this multi-resolution approach is geared toward all sorts of situations, even where you're not data-based. This is the text of a book. It's a very famous book, Bleak House by Charles Dickens, and every column is a chapter. Now, I'm doing this, I'm zooming in on a letter like this in order to show you, in order to prove to you, if you will, that this is not just an image of the entire book of Bleak House. Because if this were an image, then it would have to be several terapixels in order to produce this sort of resolution. So you know it's not an image that doesn't fit on any hard disk that I know of. All right, sorry. So what's going on here is that we're changing representations at different scales. This is demoware, obviously. When we're zoomed very far out of this book, we're dealing in a representation that doesn't represent the individual characters of text, because at this scale, when all you can see is less than a pixel for every character, it's not efficient to represent text as ASCII anymore. At this point, it's more like an image-based representation. Whereas if we start zooming in and we have an A fill up the entire screen, at this point it's no longer efficient to represent that A as pixels. We could just be sending one byte to represent the entire character A. So there are changes of representation at different scales in order to maintain that sense of efficiency across scales. And what kinds of representations you pick at what scales depends on what the data is and what you're doing with it.